Today I'll be presenting early stopping Byzantine agreement protocols. So I'll be going over the problem definition, related work, and open questions. So just to start, just the problem definition, we have Byzantine agreement where you have a set of n parties. Each party has an input and parties try to agree on a common output. Just for formal definition, for the security properties, you have validity, where if all honest parties start with the same input, then they have to output this value. And agreement, where all honest party output the same value, even if they started with different values. So this is the consensus version of it. There is a broadcast version where you have a specific sender and, PS, and parties try to agree on this sender's value. So what is really early stopping? So early stopping is mainly related to the round complexity. Specifically, you want to terminate in terms like a function of f, where f is the exact number of corruption during the execution. So T here is the maximum number of corruption that the protocol can withstand, and f is the exact number of corruption. So there is a lower bound by Dollar-Breshko-Strong that a Byzantine agreement protocol terminates in minimum f plus 2 and t plus 1. Okay, so I'll be going over all solution right now in this area in different settings. I wouldn't really give the full construction for every protocol, just the key ideas of how they solved it. So for the information theoretic setting, where you have computationally unbounded adversary, both solutions for T to the n over 4 and T to the n over 3 are based on EIG, where EIG is the exponential information gathering graph. I'm going to explain it in a bit. And they both actually achieve the optimal solution. They both have the optimal round complexity, but for the computational bounded adversary setting, none of the settings have the optimal solution. So Perry and Tuig proposed the first solution for consensus for T to the n over 2. And it is a 2-factor more than the minimum round complexity, or the early stopping round complexity. Then we proposed an improvement where we achieved f plus square root f. And for the T to the n setting, where they solve broadcasts, they have O of f square round complexity, sorry. So for T to the n over 2, you can solve broadcast or consensus, but when you go to T less than n, you can only solve broadcast. Okay, so I'll be going over both solutions, like all solutions, how it was done. So starting with the EIG-based approach for the information theoretic setting.
Sorry. A quick question on this lower bound is for both the settings.
Right. Yeah. So for the EIG-based approach, basically this was proposed by Pease and Lampert in 1980, where they were solving the setting for T less than n over 3, not early stopping, just Byzantine agreement for T less than n over 3. And they solved it using EIG. So EIG is a type of data structure or a graph where parties store information throughout the protocol as it is running. And by the end of the protocol, they are going to calculate their output based on this graph. So just to give an example, assume we are solving for broadcast, where the sender sends me a value in the first round. I'm going to start drawing my graph where I'm going to store the root node PS for the sender, and I'm going to store basically the value that the sender sent me. If he did not send me anything, I'm just going to input, store 0. In the next round, I'm going to echo what I heard from the sender. So every party just echoes what they heard. If they heard nothing, again, they just echo 0. And basically, it is saying that I heard from the sender that he sent me this. And you store, again, in all the nodes you heard from, what the sender sent. And notice that the nodes have n minus sigma children. Assume that this node is like sigma here is the depth of the node. And we start with depth 0. And basically, if you just want to store what other parties heard from the sender. So every other node that's not the sender, you want to store what they heard from the sender, what they echoed to you. And then this goes on. You just keep echoing what you heard in the previous round, and you want to store what you heard in the graph and keep going, keep the echoing basically. And again, it is just basically here, for example, P2, like this is my graph. I'm storing what P2 sent me, that PI sent him, that the sender sent PI. Is this clear?
What is sigma?
Sigma is just a notation for just any random node on the graph. Yeah. So how do you calculate the output? So just the protocol basically runs for T+1 rounds, and each path is a different node, right? Because like here you have node 1 where you want to store what node 1 sent you. And then you want to store beneath that what node 1, what the other parties heard from node 1, and so on. So you always, as I said, go for n minus sigma children. So you go down this path where here it is basically what you heard from node 1, here what you heard from node 2 on node 1, and here what you heard from node 3 on node 1, 2. Okay? Clear? Okay. And then to calculate the output, you just, after you run T+1 rounds and you store all this graph, you calculate the output by applying a function over your graph. So the value you stored in the leaves stay the same. You just keep them, where we call them a resolved node. Resolved value were basically the final value for this node. So for the leaves, their final value was whatever value you stored during the protocol execution for the T+1 rounds. And for any non-leaf node, you take the majority over its children. And then you keep applying this function recursively up to the top. Okay? And whatever value you calculate for this root node is your output value, basically. Okay? And why does this work? So I'll give a proof by contradiction, but before that, I'll just mention two main properties, or like kind of lemma, but I don't really prove them. They are straightforward to see. Where basically we define a common node by a node that has the same resolved value in all honest parties trees. Okay? So this is the resolved value, again, is what the value you calculate when you are doing this computation on the graph. And the lemma here is that each honest node in the graph is a common node. And the reason for this is because an honest node is going to send all its children the same value, right? And you have an honest majority of children for every node. So say you have node, again, sigma, you have majority of these children are honest. Just because of the t to the n over 4 or t to the n over 3. You always have some honest majority children for every node. So if the node is going to send the same value to all its children, they are all going to keep echoing the same value. No.
So if I remember that, like if a node is bad, can it claim incorrect values for all its children, even the honest ones?
Can you repeat that? Sorry.
So let's say P1 is honest, but P2 is not.
Okay.
When P2 sends all the messages, can it claim different values for all the children, even the honest ones? So for this node, wouldn't be a non-common node after that?
Right. So the malicious, but the idea here is this honest node has honest majority of children.
It's honest node.
Each honest node, right? Because The graph runs for at most t plus 1 rounds,
Yes, yes.
right? And then you have t less than n over 3 or t less than n over 4, right? So you start here with having, say, the n children. Sorry. N children, and then here you have n minus 1, and then you go down, right? But half of them are always honest, because n is 3t plus 1, right?
I see.
And you keep, or n equals 4t plus 1. The solution works for both of them.
Not 2t plus 1.
Not 2t plus 1. You need different recursive function. And then, yeah, good. Is it clear to everyone? So yeah, just because we have this honest majority of the children, they are going to echo, so P3 is going to echo the value, if it is honest, is going to echo the same value that is heard from P1. And because you have honest majority of the children, they are going to echo the same value on the honest node. And this code keeps going, and you prove by induction, basically. Okay.
Will this message size be exponential in the?
It is exponential. Yeah, it's exponential. Yeah, it's
But that's
called
okay, because the round complexity is now,
F plus 3.
okay.
Yeah, I mean, sorry, it is early stopping, but I'll show you how they get around the exponential communication, actually.
But so P3, like the P3 under P1 here is the message P1 received from P3 of what it heard. Is that it?
So,
Or is that what it's sending? Like, yeah, what
So-
does that P3 represent?
okay, so this is my graph. It is what I heard from P3 that it received, that it told me that it received from P1.
Got it.
So that's why, like, if you have honest nodes, you're always just going to echo what exactly you heard from P1. So they're going to be the same in all honest parties graphs, basically. And then, yeah, so now we have every honest node is a common node in the graph. And then we prove by contradiction, okay? Why does agreement holds here? So agreement, so as we said, you output the value that you calculated for the root node, right? This is your output value. So assume you have two honest parties that output different values. This means that the root node is not a common node, right? Because common node has the same value in all honest parties trees. So it means that the root node is not a common node. For the root node not to be a common node, it has to have at least one child that is not a common node. Because you apply the same majority function over the children, right? So for it to output a different value, at least one node is not the same in honest parties trees. And you keep going. So here for P3 to be not common, it has to have at least one child that's not common. And the proof is by contradiction because, you know, it runs for t plus 1 rounds. So you have a path of t plus 1 children, sorry, a path of t plus 1 nodes. And at most you have t malicious parties. So you have at least one common node on the path. And this is why you arrive at contradiction. The output rule is the value you resolved the root node to, and you calculate the resolved nodes by applying deterministic function over the graph. So the leaves, you resolve them to the value you store during the computation, and any non-leaf node, you calculate the majority over the children, over the resolved value of the children. Okay? The proof clear? Okay. So this is the information gathering graph. And then both papers by Garay and Itai to solve for t to the n over 4 and t to the n over 3 based their early stopping solution on this. So their main intuition is basically, you don't have to keep going down the graph. You can predict early on what the value of the node would be. And then they devise some early stopping rules so that if, for example, the node has a certain value, a certain number of children with the same value, they can easily predict the node's going to be a B. I'm going to explain later on. But this is basically the main intuition that you want to stop in your exponential graph, you want to stop some branches early on, and you want to stop them in complexity of f plus 2, or like a function of f. So this is the first insight. And the second insight is that once you are able to detect that a node is faulty, you can just ignore what it sends to you. You can just pretend that it sends you 0 and just store 0 and ignore if it sends you 1, basically. So what is the early stopping rules? So the early stopping rules, the first one is that if a node has n minus t minus sigma children with value v, I can predict that the final value of the node is going to be v. And why is this safe? So the main idea is that if node sigma is honest, I don't need to argue for it because it's going to send the same value to all parties. If node sigma is malicious, but some node on the path here is honest, I also don't need to worry too much because by the same argument of common nodes, eventually I'm going to have here a common node, and any party that did not act well down the tree, it's not going to really hurt me. And if the main argument is that what if every node on the path is actually malicious and you don't have any honest node? So if you have every node on path sigma is malicious, then you have at most t minus sigma malicious children, because you have at most t malicious children. So node sigma has at most t minus sigma malicious children, right?
So the size of sigma just, what is it, more than 1?
It could be anything. It starts like it could be one. It depends on where it is on the graph. So each node has n minus sigma children, like because you need. So here you have node 1, right? And you want to store what other parties told you on node 1. So you only need n minus 1 nodes here, right? And then you go down for TP2. You don't need to repeat 1 back again, what 1 said on 2 on 1.
Okay, so the size of sigma is the height of the sigma of the tree.
Right, right. So yeah, so if sigma is malicious and every node on path sigma is malicious, you have at most t minus sigma malicious children. So it means and if sigma is at most length 2, which is the parent of the leaf, then you have n minus 2t, at least n minus 2t honest children. And since they are honest children, they are going to be common.
But can you explain again the argument for n minus sigma malicious?
Yes, you mean the third one?
Not the 2t, this is you said t minus sigma.
Right, so I'm trying to say why it is safe in this scenario. So the first scenario, if not the sigma is honest, we're good. If we have an honest node on the path, again, it's going to be eventually be good. So the idea, if you have node sigma, and every node on the path is malicious.
On the path.
On the path.
After.
Up, all the way up. Every node on the path is malicious, right? You know you have at most t malicious parties. So for the children, you have at most t minus sigma malicious children. Okay. So if you have t minus sigma, and sigma is at most t when it is a parent to the leaf, then you have for every node, you have at least n minus 2t. And when we are in the setting of n more than 4t, you have honest majority.
Usually in these arguments, you're trying to construct a quorum, right? That's the point. The two these cases cover the specific sigma for which you will have an honest quorum guaranteed without going on to value.
Right.
And then it depends on what the relation between T and N is. And then you need to find the specific sigma, but this covers all three cases.
Right. Yeah. I mean, we have more arguments, but I'm not going more specific, just like general why this would hold.
The fastest one is the third case.
Um,
That one highest in the graph, the third case.
no, but this will take you at least F rounds, right? It will take you because at least F rounds till you close it. This one is the fastest. It is the fastest because here in this rule, n minus t minus sigma, right? And I know if you have an honest node, so as I said, each node has n minus sigma children. At most, t of them are bad. So you guarantee once you have an honest node, everyone is in the next round. Because everyone is going to receive those many children with the same value. Okay?
At least in the case. And this makes a quorum directly
Right,
and independently of what sigma is.
right.
Sigma can be up to F, absolutely. So
To t. I mean, it's up to t plus 1, but if you are looking at the children, then you look at the one before the leaf.
I didn't understand how they can decide before. So you're saying they can decide before T plus 1?
And it's like we are predicting that this is going to be the final value of the node, and I wouldn't have to keep going and echoing.
But why would different parties see the same view? Like, what is the argument there? Like, why is it that, okay, so somehow one party might see, I mean, yeah, why is that case just not possible? That one party determines that, oh, I want to stop in the next round, but maybe party two doesn't know if it's time to stop there.
Right.
Like, this cannot happen for some reason.
No, it can happen, but the idea before that, it was safe in all cases.
What does that mean?
So, okay, I can repeat that. So the reason for why it's okay to just stop, although some other parties may not see the same thing and might continue on their own,
Right.
and I might stop earlier than them. But
Okay, no, so I guess that was.
it can happen, it can happen, yeah.
how much? Like, is there a limit on how much? Like, is it around earlier or is it like
No, it can be more, depends on F, basically.
If I decide to stop as an honest party, then the other honest party keeps going, do I still respond to the honest party?
No, you
I
don't,
don't that.
no, you
You
don't,
have to figure it out without.
based on the, yeah, how you are silently.
when you stop for that specific part of the tree only, right? The subtree.
Subtree,
So you send message, you keep sending messages for the rest of the.
the rest of the
Okay,
nodes.
so. Basically, once you're honest and you've stopped, you have sent the last message, you would send nonetheless from that tree, I suppose.
You just echo one more round on the children and then you stop afterwards.
Even if you kept going, would you send more messages?
Not on this subtree,
Think about this.
not this one subtree, the subtree is after that. Okay. Okay, and then and the second early resolved rule is basically if you already resolved the majority of the nodes, then you can resolve the current node as well. And the intuition behind this is when you have say the F path, right? And then you have honest node closing here. You would want to stop. And to stop, you need to be able to calculate the root node. So the reason for stopping is when you are able to output a value, right? And say after the F path, you have only honest children, and you're going to resolve them in round f+2. So you want to be able to calculate up the path, to resolve nodes up the path. So every time you are running the graph, you resolve nodes, and you try also resolving up the tree. So this one is just for resolving a node and the children. This one is to be able to keep going up more. If you resolve the children, then you can resolve the node, and if you have more nodes here resolved, then you can resolve the parent, and so on. Okay. And then once you're able to resolve the root node, you calculate the output, you can just output this and stop. Is it clear? Is it confusing? What's confusing?
Say what the rules are for resolving early, depending on the subcases. Still have some rules, but this is simple, right? I mean, the main argument is that you need to figure out majority for a node, and then you can resolve. If you have majority of a value already, you can resolve it. You don't have to wait for the rest.
Right.
That's fine. This is an easy argument. But the other arguments, how fast can you resolve, depending on the depth and how many bad nodes you can predict.
Right.
I think this.
I mean, I'll need to go through more proofs, but we can discuss afterwards. Yeah.
So when you do the first one is a stronger value.
Yes, for the number of children.
It's always majority, but it's really super majority depending on sigma.
Right.
And you cannot apply that rule. And then in order to go up, you need to apply
The second rule. And the reason of this, like, if this rule is safe and you have common nodes or resolved values that are common and safe, then you just need the majority, right? Because if a node is resolved and it is common, then all parties are going to have the same value for the common nodes.
Yeah, for the second rule, we don't need as many.
Right.
As the first.
Right. You just if you have common nodes that are majority, they're going to be the same in all honest parties trees, and then you just keep going up.
So in the ideal is a early stopping party should resolve the root node after f+2 rounds,
Right.
like always, or in the weak case?
No, always to have a round complexity minimum f+2 t+1, you always have to put it in f+2. So like in the end of every round, you try resolving, you try applying the rules, and if you calculate the root node, just stop. If not, you have to keep going, basically.
Yeah, that most to go to f+2.
Yes. And the other rule is just for detecting a faulty node. And the main idea here is because of this rule is that, as I mentioned, whenever you have an honest node, you're going to have this many children. Like this rule can be applied because the node, say sigma, it will have n minus sigma children. At most, t are malicious, right? So you're going to have this enough nodes with the same value of an honest node. So once you have the honest node, you can just resolve it in the next round directly. Okay. So if a node is not resolved by the end of the next round, it is malicious. Okay. And you add it to basically like you maintain some faulty lists, and you add it to your faulty list, and any value, any future message you receive from this party, you just store value 0 in this node. I mean, this is like, I'm not going very in details, but the whole idea is basically they come up with rules where you can just stop the graph, although it is exponential communication, the graph can stop in minimum f plus 2 t plus 1, and you don't have to keep going. You can close the branch. You don't have to keep echoing on the subtree with this root node. Okay. For the T over 4, it is the EIG is f plus 3, just because you have to echo for one more round on the children before closing, but then they show a way to get around this extra node. So if you have f malicious, then you have f plus 1 honest nodes. They don't necessarily have the same value, so they don't necessarily. You can't easily basically resolve this node because it is malicious. You don't know what it sent to parties, but you know all these children are going to be honest. You know that you're going to close them in the next round, and then you need to echo one more round and stop on the children. That's why you go to f plus 3. But yeah, they have a rule where basically you can just get f plus 2, which basically you just need to check if your faulty list is less than r plus 1 or not. It's like they are forcing the malicious part or the adversary to spend one malicious node party per round, and you add a new node in every round. I feel I'm losing you guys, but yeah, it is just trying to close the tree early using some early resolve rules. This is the end idea. But this is exponential communication. So how do they get polynomial communication? The idea here is that if you have validity, by validity is that if all honest parties have the same value, the same initial value, they all need to output this value. So if indeed all honest parties start with the same value, then again, you are going to just echo one more round, and then you will see that you can able to resolve the node, because basically you have n minus t honest children. If they all have the same value, then you have n minus t of these children to be the same value. Okay, and then by the early resolve rule, you have to have at least n minus t minus sigma children to resolve the value, and sigma here, lambda here is just depth 0 or height 0, and you will have n minus t nodes with the same value, so you can resolve this node in the next round, basically.
You mean if validity false? Validity always false.
I meant if you have validity. Sorry.
It should always have.
No, I'm sorry. I meant basically if all honest parties start with the same value. So if you have this, the condition to have validity, if all honest parties have the same value, then you are closing within 2 rounds, right? Because again, it is just by the early resolve rules. You have n minus t children with the same value. You apply the rule that I mentioned before, and then you can just set the tree directly, the output, and just output the value. So the main idea, if you have validity, then you can terminate in 2 rounds. Okay. So if the protocol runs for more than 2 rounds, then we don't, sorry, maybe it's bad writing, but basically then it means we did not start with the same value. Okay. So if we run for more than 2 rounds, we know we did not start with the same value, then we can just terminate with any value. I don't care what value I terminate with. It can be a default value. I just need to have agreement that we're all defaulting to the same value. Okay? Any questions? Okay. Good. Okay. So what do they do is basically they start a new early stopping EIG in every round. So in the first instance, you don't know the initial value. In the second instance, you don't know the initial value. But if you keep running and you know you're not terminating by the end of the round 2, then you start inputting 0. 0 is basically the default value that you want to stop on. So you can think of it that we are debating basically. Should I stop? Should I not? In the beginning, I don't want to stop, so I'm just using my initial value. By round 3, I want parties to stop, right? So I'm saying let's stop. I'm gonna input 0 and let us not continue with the graph because you want to have polynomial communication. So the idea here is that because if parties go to the 3rd round, all of them, and they did not terminate, all of them will have input 0. And if all of them have the same input value, they are terminating within 2 more rounds. Just because of the thing I mentioned here, is that you will terminate within 2 rounds, right? So if everyone inputs 0, they're going to terminate within 2 rounds. And once you see an output of an EIG is 0, you output 0. Okay, so your final output is basically the minimum of the outputs of all instances. And that's why when you see 0, you can know that you can safely terminate.
I don't understand why there's one instance not enough. So maybe I miss important part here. So on the previous slide, we have like one protocol that. So what is this EIG guaranteeing for us? This 2-round protocol, basically a 3-round protocol max, or no?
Yeah, the reason is that you might have different input values in this one, right? You might have different values, so you need to start a new one in case you do not terminate with this one.
So in three rounds, you quit that one. So
You don't quit, you're actually running all of them. You are starting a new instance in every one. You're starting a new instance every one, but your initial value changes based on whether the protocol is still running or not. And the reason you have to keep going until you receive an output from one of them is that you cannot just start this one and stop because you don't know what is your input here. You don't know whether you have agreement. This one can continue running for some time. So you cannot just stop at round 3. It depends on what the malicious parties can do, because you can have F more than 3. The main idea is that you keep starting instances, and once one of them terminates with 0, you know you are good. You don't have to keep going with running all the instances, just because you have agreement guarantees per EIG instance. So every EIG instance has agreement and validity,
right,
and runs for F+3 T+1 rounds.
Okay.
But it has exponential communication. Okay? And the idea here, if I'm running for more than 2 rounds, I know I don't have validity and I want to stop. So what happens in round 3, I want to tell parties to stop. Okay? So you can have, you input 0, and if any of the instances terminate with 0, then you don't need to keep running any of the previous ones, because you know that the honest parties are going to get the value 0 for this one.
But you're saying I'm broadcasting 0 for everything that for all my messages.
No, just for your input value. So you have your input value.
Every round you're running an instance of that protocol.
Yes.
So in round 2, I'm basically, or maybe say round 3, I'm running the second round of the instance I started in round 2.
Yes.
The third instance of round 1.
Yes.
Yes.
It's like, yeah, concurrent.
And concurrently starting. And the idea is that in the 3rd round, if I have not terminated my first instance, that means we didn't have validity.
Yeah.
And therefore just send 0 moving forward. And if okay, or we terminate, but then yeah, I don't understand why we need to go further rounds. Like at round 3, I can already know if my round 1 protocol terminated or not, right? And if it has terminated, then I know we have an output. And if it hasn't terminated, then we didn't start with the same input. So just stop now and say the output is 0. Why can't I do that?
Because you're not sure that other parties have the same view.
They should if we started with the same value. That's what you showed in the previous slide.
Right, yeah, if you show the same value, then you're going to output the same value.
Okay, so maybe even if they didn't start with the same value, it doesn't matter. They might end up with the same value.
Right.
Which is the reason why you want to control.
So is this guarding against like honest nodes getting some messages by malicious nodes and making them think that you have them in the first 2 rounds?
Yes. Wait, no, repeat this question, sorry.
Yeah, basically what Varun asked. So like if you're honest, like at least one, if you don't have a limit, at least one honest node will realize that by round 3, I assume,
Yes,
but not all of them at round 3.
right.
So because some of them might think by end round 2 that they have a limit.
Right, so you might output some of them, so the output is not at the same round, right? Some parts might output earlier than the others, right? And then we need to keep going. So here, some party might have received output value 1, right? But then you need to keep going in case the input value is not the same.
I guess the guarantee on the previous slide is really confusing. Like you're saying on this 2-round protocol, like what exact? So what do we know after 2 rounds?
What do we, after 2 rounds?
So this EIG is a 3-round protocol.
No, it's F.
The full protocol.
Okay, it's
protocol.
It's just that after 2 rounds, you know that if you keep going, you didn't have the assumption of the validity protocol. So you didn't, not all of you parties started with the same value. And you can defer that if you keep going up 2 rounds. You know, not all of parties started with the same value. That's the only thing you can tell.
And in this case, all I need is basically for all honest parties to output.
The same value, you need agreement. So you now start out inputting 0. And you assume that every other honest party will have the same, that made the same understanding of the protocol, they output 0 going forward. I also have a question, which is, we have 2 questions. One, why do we need round 2? Like round 2 doesn't fit to cover anything. Like if you start with your value in round 1, you didn't terminate after the 2nd round, or you keep going in round 3. Why do we need the round 2? You have already an instance with this value, basically, that will either terminate or not. You don't get any additional information from round 2. And it will not finish earlier than round 1 either, because all of the parts start with the same initial value.
This is true.
It's fine, that's.
I'm not completely sure about this, but yeah.
But I still don't understand the guarantee. Like, so the guarantee is some honest party will notice, or all honest parties will notice.
All honest party will notice that you're still running, but some of them might have an output here with 1. So it depends. You can have different views
They
based.
might already have output something that's
Right, yeah.
That's my second question. So what prevents the agreement from breaking? Like what prevents the case where one honest party stops with agreement on the initial value, let's say? No, with agreement on some value, not necessarily the initial, from the AG of the round 1, in let's say round S. And then not everyone stops at the same time. And now let's say that another honest party stops from the EIG of round 3 without value 0.
Right.
The next round.
Right.
How do we prevent from this happening?
So if parties are silent, you assume they are sending you 0.
But how do you guarantee agreement after that? Like if I'm silent because my EIG finished in round S
Right,
and we output value 1,
right,
and not everyone else's EIG finished at EIG of round 1 finished at round S. Someone else kept going and they finished in the next round, exactly the next round, let's say it's at the EIG of round 3 without 0. How do they cover this corner case?
sorry, it's slowly repeat again.
Sure. So imagine that we start not with the same value,
Okay,
And say that EIG of round one finishes at some random round S
Okay.
for one party, on one honest party, and you finish with value one.
Mm.
And now there is a bad case of in the next round, EIG of round 3 or 4, it doesn't really matter, for some other honest party, finishes with value 0.
Right.
Now you don't have agreement, right? You have two honest parties seeing different values of EIG first.
But you have agreement because the EIG instance. So even if you stop with one, you know that you're trying to stop with 0 here as well.
Afterwards.
Yes.
So how do you cover this? Like what you output eventually?
So you output, you mean one, the party here output 1?
So I think the question is, do all parties have to run for K rounds? Like you
No.
run in K?
You don't run for K, you run one, like once you have the output, then you stop.
But if you start with, that's my question. If you start with that value, then it can happen that I start with 1 because that's what finished first for me.
Mm.
And in the next round, another honest party starts with 0 first. It just happened, like, or is there some ordering that you apply? Perhaps if you have ordering on the EAG's round.
So if you run at least 3.
No.
Still happen.
No, you always output the minimum of the values,
The minimum.
the minimum of all the instances.
If you see 0, you can stop because 0 is the,
Right.
but if you don't,
Yes,
you
exactly.
need to.
But this means that if you see 1, you cannot finish. You wait to see 0 terminating around K. So how do you cover that?
Round 3.
No, you can see 1 even if you don't have, hold on, first, I will see the value. You can still have the output one, you can see the first as well, so you can see how that's.
I think you output something for every EIG. Each honest party outputs, gives an output for every EIG.
I
And they
think
output the minimum.
you have the polynomial communication, and that's the whole point, right? You need to be able to finish as fast as possible. Not to complete all EIGs, and maybe just increase.
No, okay, I'll tell you, because if you have validity, I'll tell you the idea is if you have validity with 1, you are terminating within 2 rounds, and everyone's terminating within 2 rounds. If you are going and you terminate with 0 afterwards, it means you did not have validity. So when parties take the minimum, it is safe to output 0. So if you have validity, you can either have validity with 1 or validity with 0. If you have validity with 1, you all terminate in round 2, right? If you don't have validity, then you are inputting 0, right?
You done it on 4.
And then you are done. And then you are done with round 4, but it depends on the views here as well. The reason is that you are running for more instances that you might have different views here and here as well, in the different instances.
What is K? I mean, okay, I guess the question is, what is K? Like, what does K depend on?
You're starting a new instance, basically.
Yeah, no, so is there a number to K, like, is that polynomial in?
It's an F,
Is F,
polynomial in F, basically, if you are starting a new one.
K is polynomial in F.
But the protocol anyways, I think this was what's confusing guys, but anyways, it's going to terminate by round 4 or 5.
Right.
If
Because at round 3, you have validity for 0, right?
right,
You're starting round 3 with every honest party starting with 0. So that must mean that by round 5. all
no,
honest parties.
but it cannot be true.
Right, they might have finished, but they will still start a protocol with with input 0.
But then you always output 0, right?
No, unless everybody has started with the same value, then you output that value, because
Yeah. Exactly, that's the question, that when you see 1, you need to know that you can stop with 1, otherwise you will keep going and 0.
oh, really? Wait, wasn't that what you said in the previous slide, that if everybody starts with the same value, then you terminate into 1?
Right,
Everybody terminates.
right. So if you have, yeah, so if you have validity with 1, you know you're terminating in round 2. So you want to break validity if you start a new instance. You're not starting a new
It can
instance.
happen that you finish with one, that's it, it's a counter, like, you can finish with one as an honest party without everyone starting with one. Because it depends on the share value, so you can imagine, half of the honest party starting with one, half of them with zero, and then the share values are all one for one instance of the honest parties, and random for the other honest party. You do not know.
No, but then you are starting a new instance with them. You don't
Yes.
stop with, like, even if you output one, you don't stop, right?
Okay.
And if another instance are running,
If
the
you
on-
don't stop, then the question is, how do you finish with one? How do you, because otherwise, if it's the minimum, you, as we said,
right.
after round three, everyone's guaranteed to finish with zero.
So you output one in one instance, right? It's not necessarily you're outputting one in every instance, right?
Yes.
But say you output one in this instance and other instance are starting. So you are starting with them and you are starting here with zero, right? And once you have output zero, then you take the minimum over them and you also output zero, even if you had one before.
But then everyone will always output zero.
But this is the default value if the protocol is running for more than 2 rounds. Because it's like you don't need validity anymore and you want to terminate on a default value, which is 0.
What you described as an algorithm now, everyone will run round three, because even if you see one, you're not guaranteed that everyone saw one. Are you guaranteed? Like perhaps we missed this.
You mean validity?
Yeah, if, maybe
Not
not
just validity, like the honest party view, let's say after round two, I'm an honest party and I terminate the protocol with value one.
What do you mean terminate the protocol?
I saw a majority of values, like I decided on all the vertices on value.
This is
up
just
to-
one instance.
Yes.
You don't terminate when you have one instance terminating. You terminate in 2 cases.
Yes.
Either all instances terminated or you have a minimum of 0. Or you have output 0. So you only have 2 instances to terminate.
But if all instances terminate, you always output zero.
So there's a case where everybody terminates by round two, and then nobody starts once. So somebody has to start round three.
Okay, so it's not clear how you decide to start the next one.
You started with sound if you haven't found an output background.
I think that's the point of that
Yes.
second
Okay.
instance of the ESEIG. So the
Okay.
first instance, people have terminated in round one. They say, okay, I've terminated my first instance. Then you start the second instance anyway of round two. And then again you terminate, say, in round three. Then you're guaranteed for some reason that, okay, now everybody has started with the same value and we can terminate. No need to run round three. But on the other hand, if one of those has not terminated by round three, then you start with 0 in round two.
Even the termination, it takes at least 2 rounds, right? So 2 rounds will not take effect for starting round three.
No, it will take an effect here. So if you all do the same value with 1, you're all terminating here.
End round.
At the end of round,
Yeah.
So they won't start round.
yes, from round one though, not from round two.
But the round would do the same thing.
For round four, you mean?
Yeah.
But you would have it from round one already, right? If round
Yes,
two
maybe
is
it's
in
not,
round four, you would have it from round one.
Yeah, at the end.
Round three. That's a detail, yeah, that's very, it could be that it simplifies the description a bit like that and not remove round two, so even for that, it would be valid.
That's okay. I did not have time to go over the rest. Okay, so yeah, I mean, there's still open questions, I guess, for the computational setting. Yeah, it was a way longer PowerPoint meeting. I did not manage my time correctly. If you have any questions or wanna see any constructions for the other ones, I'm happy.
Right, so your main result is what? That.
The F plus square root F.
I see, so you show that, and is it based on this exponential stuff?
It is not. So we show actually 2 solutions. We have a solution for EIG that gets the optimal, but we could not do it in polynomial communication. It has exponential communication. And the reason for this is, quickly I'll mention, sorry, we don't have this validity rule. So for us, even if you have the validity or if all parts have the same value, you are still terminating in round F. You need to terminate within constant number of rounds to be able to do this different instances and try to debate whether you want to stop or not. So we did not have that. But yeah, we show both solutions that we can achieve optimal, but it's exponential communication. And yeah. Thank you.